Hello and welcome to all. In this lecture, we are going to discuss the pumping lemma concept. So we know that generally there are two types of language. One is regular language, another one is non-regular language. So regular language that we can represent with the help of regular expression, as well as we can draw its equivalent finite automata. But there are some language which are not regular. We cannot represent such a language by means of regular expression, as well as we cannot draw its equivalent finite automata. So first of all, we need to prove that the given language is not regular. So for that, pumping lemma is useful to prove that the given language is not regular. So what do you mean by pumping lemma? It is called as pumping because we pump more stuff into middle of the word, swelling it up without changing the front and back part of the string. This indicates that we are going to keep the front part and back part of the string as it is. Only middle part of the string will be repeated number of times. And lemma is a Greek word. It helps to prove that certain languages are not regular. Pumping lemma which uses pigeonhole principle. Now what do you mean by pigeonhole principle? So according to the pigeonhole principle, if there are m number of holes, and n number of pigeons are there, such that if m value is less than n, its number of holes are less than number of pigeons, then there are some holes which will going to hold more number of pigeons into it. If I'll say that m is equal to 4 and n is equal to 8, m is equal to 4 and n is equal to 8, then here there are so as there are 4 holes are there, so each hole will going to hold the one pigeon into it. Let us consider number of holes, pigeons are 5. Okay, then at least one hole will going to hold the more than one pigeon into it. So same way pumping lemma will work. There are some states which will going to repeat the particular part. Now definition of pumping lemma. Let L be the regular language. So as L is the regular language, so there exists some finite automata m which will accept the given language. So m is equal to, we know that finite automata is represented by using 5 tuple capital Q, summation, delta, initial state and final state. So these are the 5 tuple. With the help of that we can represent the finite automata. So Q indicates that the finite non-empty set of states, summation set of input alphabet, delta is the transition mapping on next state function, Q0 is the initial or start state of the machine, and F is nothing but the final state. Then there exists a constant n such that for every string w in L. So whatever w is there, if that string belongs to the L, then we can say that that string is in the regular language. Now mod of w means length of w, the string which we are going to consider must be greater than or equal to n, some constant value. Now we can break the w into 3 strings such that w is equal to x, y, z. Now what do you mean by x and y and z? Here mod of y means length of y, middle part of that particular string must be greater than 0. Second, mod of xy is less than or equal to n. And third important condition is for all I greater than equal to 0, the string x into y raised to I z is also in L. Means if I say that x, y, z, it must be in L. x, y raised to 1, z, it must be in L. x, y raised to 2, z, it must be in L. Where y raised to I, here instead of k, y raised to I denote y is repeated or pump I number of times, means this y part is repeated I number of times. Now application of pumping lemma. So pumping lemma is applied to show that certain languages are not regular. Pumping lemma are useful to show that the certain languages are not regular. It should never be used to show that a language is regular. Okay, and this line is important. It should never be used to show that language is regular. It is useful to prove that given language is not regular. If L is regular, it satisfies the pumping lemma. If given language is regular, then it must satisfy the pumping lemma. It must satisfy these three conditions. Mod of y must be greater than 0, mod of xy must be less than equal to n, and for all I greater than equal to 0, it must belong to x into y raised to ij must belong to the L. So if the language is regular, it must satisfy the pumping lemma, and if L is not satisfied, this language is not satisfied the pumping lemma, then it is not regular. So important thing is that pumping lemma is useful to prove that the given language is not regular, but it should never be used to show that language is regular. Okay, if language is regular, it will going to satisfy these three conditions, pumping lemma's condition, definition of pumping lemma. But if L is not satisfying the pumping lemma's three condition, then we can say that it is not regular language. It's non-regular language. So these are the steps or algorithm to convert the given to check the given language is not regular. Okay, at first we have to assume L is regular. So here we are going to apply the contradiction method. Initially we are going to assume that even the given language is not regular, still we are going to assume that the given language is regular one. So the pumping lemma should hold the L value. Means if it, as I said that if language is regular, then it will going to satisfy all three conditions of the pumping lemma. So if we are going to assume that L is regular, then it must so that pumping lemma should hold for L, given language, regular language. Use the pumping lemma for to obtain the contradiction. Now we want to prove that the given language is not regular, then we need to apply all these conditions, and we have to obtain the contradiction. If contradiction true, then we are going to say that the given language is not regular. Now we'll see one example. With the help of that example, we'll see the definition of the pumping lemma and what is use of pumping lemma. Using pumping lemma for regular set, prove that the language n is equal to 0 raised to n, where n is a prime, is not a regular. So we know that prime number means the number which is divisible by itself and 1. So I'll say that let us consider some example. 0 raised to 2, 2 is the prime number, we know that. After that 0 raised to 3, 3 is the prime number. 0 raised to 5, so 5 is the prime number. After that 0 raised to 7, 11, okay, 13. So like this, all these are the prime number. Now, so we know, so we can represent 0 raised to 2 means L is equal to like this. L is equal to 2 0. After that 0 raised to 3 means 3 0. 0 raised to 5 means 5 0. 0 raised to 7 means 7 0, like this. Okay. So we know that we cannot represent this type of language with the help of regular expression, as well as we cannot draw its equivalent finite meta, which will represent the given language or which will accept the given language string, all string. Okay. So now we want to prove that the given language is not regular. So according to the algorithm or method of the pumping lemma, first of all we are going to assume that the given language is regular. So let us first step, let us assume that the language is regular and accepted by the finite meta with n number of states. So we are going to assume that the given language is regular one and it is accepted by the finite meta with n state, where n is some constant value. Now let us choose some string w which belongs to the given language or which belongs to the regular language. So let us say w is equal to 0 raised to p. W is equal to 0 raised to p. Then what is the length of this 0 raised to p? It will be mod of 0 raised to p, and that is equal to p, such that p is greater than equal to n. Okay, if I say that p value is 4, then length is what? 4. As it is a prime number, so it will be either 2, 3, 5, 7, 11, 13, 17, like this. So that's why the mod of w is equal to 0 raised to p is equal to p, where p is greater than equal to n. Now next step is nothing but we are going to break that w into xyz string, such that mod of y must be greater than 0, mod of xy must be less than equal to n, and so mod of y, first is, let us write w as x y z with mod of y greater than 0 and mod of x y is less than equal to n. Here we can assume that y is equal to 0 raised to m. So total string is 0 raised to p. So out of 0 raised to p, we are going to divide that 0 raised to p as a x, y and z part. Okay, where y is nothing but some part of 0 raised to p. If I say that total 7, 0 raised to 7 is 7 7 is the length of that particular string. Out of 7, let us say 2 is the length of y. So it will be 0 raised to 2. So I'll say that 0 raised to m. Okay, where m is equal to suppose 2 out of 7. So m is nothing but some part of the p. Okay, such that m value is greater than 0. Now we are going to calculate the length of x into y raised to I z. That will be written as mod of x into y raised to I z is equal to mod of x y z plus y raised to I minus 1. Mod of y raised to I minus 5. We know that y into y raised to I minus 1. So we need to perform the index addition. So here we will get it as a y raised to 1 plus I minus 1. Okay, so here 1 will get cancelled, that is nothing but y raised to I. So same thing we have written here. We have separated that y raised to I such that x y z, first y value will be here and remaining y raised to I minus 1. So we know the length of x into y raised to z. What is the length? Because here we know that w is what? X y z and its length is p. Okay, so that's why mod of x y z is p plus y raised to I minus 1. So total y value is m. Total y value is m, and here we need to subtract I minus 1 from it. Okay, I minus 1 from it. That's why this one is the length of this I minus 1 into m. As y mod of y is 0 raised to m, which is equal to m. Now fourth step is, now we have to check whether all these string, okay, x into y raised to I z for all I, for all y, this is belongs to the given language or not. So for that, let us put I is equal to p plus 1 here. If I put I is equal to p plus 1, then it will be p plus I minus 1. So I minus 1 is p plus 1. Instead of I am going to put p plus 1. P plus 1 minus 1 and into m. So here 1 will get cancelled. So it will be p plus pm. That will be equal to p plus pm. Okay, and if I'll take p common from this one, then I'll get p 1 plus m. So p into 1 plus 1 is not a prime number. Why it is not prime number? As we know that every prime number which will consist of two factors, one is 1, another one is number itself. Okay, because all prime, what do you mean by prime number? The number which is divisible by itself and 1. So there are two factors are there for each prime number. One factor is equal to 1, another factor is equal to number itself. Okay, so at least one factor must be equal to 1. But here we are getting two factors. One is p and second one is 1 plus m, and both are greater than 1. Why both are greater than 1? Because we know that what do you mean by m? M is nothing but mod of y. Okay, 0 raised to m. So that is nothing but y, and such that m is greater than 0. Okay, m is greater than 0. So greater than 0 means even if you consider its value is 1, at least 1. Then 1 plus 1 it will be 2. So one factor is 2. Another factor is what? P. So p is nothing but total x y z. Out of x y z, y is 2, so p is definitely greater than 2. So it will be, if I will say that remaining part is 1, then it will be 3. So we are getting both factors are greater than 1. That's why we contradict ourselves and we are going to say that the given language is not regular. So x into y raised to p plus 1 z not belongs to the L, hence by contradiction the given language is not regular. So like this we can prove that the given language is not regular by using the pumping lemma. So I'll stop here. Thank you.